Guided exercise number 2. The position of a particle moving along a straight line is given by s equals t cubed minus 6t squared plus 9t, where t is greater than or equal to 0 and t is in seconds and s is in feet. Part A says determine the velocity of the particle at time t. The velocity is the derivative of the position function. So it's the derivative with respect to t, this time t is our variable, of t cubed minus 6t squared plus 9t. So that's going to be 3t squared minus 12t plus 9. And let's see, the units should be feet per second. Part B says determine the position, velocity, and speed of the particle when t equals 2. So the position is given by s, so we need to do s of 2. So it's going to be 2 cubed minus 6 times 2 squared plus 9 times 2. And that's going to be feet. And I actually don't care what it works out to be. Whatever that is the position when t equals 2. And then the velocity at 2 is going to be 3 times 2 squared minus 12 times 2, and then plus 9, and then the units there will be feet per second. And since I need to take the absolute value of the velocity to get the speed, I'm going to go ahead and simplify that. So let's see, this is 12 minus 24 plus 9, so that's negative 3 feet per second. And so the speed is absolute value of negative 3, which is positive 3 feet per second. Part C says determine the position of the particle when it is stationary. And at an instant when the velocity is 0, we say the particle is stationary. Essentially, that is the definition of stationary. It's whenever the velocity is 0. And so the velocity that we have is 3t squared minus 12t plus 9. So I'm going to try to factor this before I set it equal to 0. It'll help. I'll show you. So let's go ahead and factor out a 3, and then this is t squared minus 4t plus 3, which is 3 times, okay, I can factor this as t minus 1 times t minus 3. Double check by foiling that I did it right. I did. So if we want to know the position of the particle when it's stationary, we need to look at this velocity and figure out the time when the velocity is 0, and then plug that into position. So the time when velocity is equal to 0, we get from setting the velocity equal to 0 and solving for time. And because we factored, we essentially did all the work already. So one factor gives us t equals 1, and one factor gives us t equals 3. And these are times. And the problem says determine the position of the particle when it's stationary. So we need to take those times and plug them into the original function, the t cubed minus 6t squared plus 9t. So the positions, s of 1 is going to be 1 cubed minus 6 times 1 squared plus 9 times 1, which works out to be 4. And the units here are feet. And then the other position is s of 3, which is going to be 3 cubed minus 6 times 3 squared plus 9 times 3. So let's see, this is 27 minus 54 plus 27. No shame in using a calculator here, which works out to be 0. And so the positions of the particle when it's stationary are 4 feet and 0 feet. Part D says, when is the particle moving in the positive direction and in the negative direction? Because we've already worked out when the particle is stationary, we can use that to answer this question. So it's stationary at t equals 1 and at t equals 3. And generally speaking, a particle can only change direction when the velocity is equal to 0 or when the velocity does not exist. But at least for the times we care about, our velocity exists, and so we don't have to worry about any direction changes where the velocity doesn't exist. So we only need to focus on when the particle is stationary. And so what we can do is we can make a chart. Remember, time starts at 0 in this problem, and I typically use open intervals when I'm talking about direction of motion. And so I'll make open intervals 0 to 1. 1 is my first time when it's stationary. And then 1 to 3, 3 being the second time it's stationary. And then 3 to infinity because it's not stationary ever again after that. And so whatever the particle is doing, it's doing it consistently on each one of these time intervals. And so what we need to do is we need to test a single value within each time interval. Here also, it will help us that we've factored our velocity. So we're going to make a chart, we're going to plug something into V, we're going to look at the sign of it, SIGN, and then that's going to tell us the direction of motion. So the direction of motion of the particle, which is what we ultimately want. So I'm going to use the factored version of V, which was V equals 3 parentheses t minus 1 times t minus 3. Because it's going to make it easier for me to tell whether something is positive or negative. So I'm going to do V of a half, and that's going to be 3 times a half minus 1, so negative 1/2, and then a half minus 3, which I'll just write as a half minus 3. It's going to be negative. So now to figure out the sign of the velocity overall, I have a positive, specifically 3, times a negative, times another negative. So overall my velocity is positive. So my direction of motion on the time interval 0, 1 is positive. And now I'm going to do the same thing, but for the other two chunks. It's super helpful that we factored our velocity because that's how we know that when we do positive times negative, we can go, okay, we can count the minuses and say, all right, the overall result has to be positive. If we hadn't factored, we'd have to do a lot more work to figure out exactly what V of a half is. Whereas we really don't have to know, we just have to know each factor, whether it's positive or negative. So on the next chunk, I would do V of 2, which is going to be 3 times 2 minus 1, which is 1, times 2 minus 3, which is negative 1, again plugging into my factored velocity. So I get positive times negative, so overall negative. So the particle is moving in the negative direction on the interval from 1 to 3. And now from 3 to infinity, I would probably do like V of 4. I would definitely pick a whole number. So V of 4 is going to be 3 times 4 minus 1, which is 3, times 4 minus 3, which is 1, so I get 9. since I can tell it's 9, I don't have to count negatives or anything. So I get positive, and the particle is moving in the positive direction again. Often your particle will change direction at those stationary values for t, but not always. And so we could have gotten positive, positive, positive on this one. We just got positive, negative, positive. Part E says make a rough sketch of the graph of s equals f of t. And we can do that based off of what we know in the first part, because we already know that the graph, so the particle, so let's think about how this goes. We're going to have t on the x-axis now, and then we're going to use the y-axis to graph the position. So our y values are going to be our original function, which I forgot now, t cubed minus 6t squared plus 9t. And we already know based on the previous part that the position is moving in the positive direction, and then the negative direction, and then the positive direction. So the particle is moving in the positive direction, negative direction, positive direction. In terms of your graph, positive translates to up on the y-axis. And so based on what we've already done, we should expect a shape that goes positive direction, negative direction, positive direction. And so to figure out exactly where to pin things down, we need to look at the position at time 0 to figure out where we're starting, the position at time 1, and the position at time 3. The position at time 0, when you plug in t cubed minus 6t squared plus 9t, you plug in 0, you get 0. And the position at 1 is 4, and the position at 3 is 0. And we have a polynomial function, and so that means that we really know a whole lot about how those work in general. Polynomial function. Sometimes spelling is hard. So we know that we're starting here, and then we need our position values to go up to 4. So I'll just decide that that's 4. And then we need t equals 1 and t equals 3. So our position at 1 is supposed to be 4, so we'll mark 1, 4. And then we know we're going to do something like this. And then at time 3, our position is supposed to be 0, so we'll be down here. So we have to go down to 0. And then the particle moves in the positive direction again forever, and we know it's a polynomial, so it has to go up like this. So there's a very rough sketch of the graph of s equals f of t. Again, particle motion that is in the positive direction translates to moving up when you're looking at the graph. So the particle, its graph goes up, down, up, because the motion is positive, then negative, then positive.